Okay, let's implement this sequence-to-sequence model together. So these are basically, this model is basically an interface for encoder and decoder. And what we need to do is just define the correct encoder and decoder, and then use those encoder and decoder we defined to perform sequence-to-sequence transformation process. We're going to define encoder first by passing V, D, and H, and decoder as well. And we also need to define softmax to calculate loss. And we need to collect parameters, and this softmax layer does not contain parameters to learn. Therefore, we just need to collect parameters from encoder and decoder like this. We also need to collect gradients, encoder, grades, decoder, grades. And how do you calculate forward? We first need to define the data we're going to input to decoder and the correct label. So decoder TS and decoder XS like this. And this is similar to language model. We need to divide this one up to the -1 position, and this one from the first position, okay? Because the first input is going to be the first input. However, the second input is going to be the first output. Therefore, this TS from 1 to last is going to be the set of all the outputs. And this one from the first to the second last is going to be the set of the inputs we need to put into the decoder. And we first calculate the last hidden state from this encoder. We pass this XS. Here, this is the source sentence or source sequence, and this is the target sequence. And we first pass the source sequence to our encoder. And this H encodes the information of the input sequence. And then we calculate score by passing this decoder XS and H. Why do we need to pass this H from this encoder? Because we are going to set the first or initial hidden state of the decoder RNN as the last hidden state of the encoder. And after that, we calculate loss by comparing the score and the decoder target sequence like this. And we return loss. And how do you calculate backward? Because everything is modularized, we just need to pass the correct value. Because the softmax is the last layer, we first pass through the softmax layer. And then we go through decoder. And then encoder. The return D out. And in the case of generate, we first encode the input sequence using our encoder, and sample using our decoder. We pass the last hidden state of the encoder and the start ID and sample size. And then we return sample. Okay, so it's quite easy to implement this sequence to sequence. Okay, and from now on, I'm going to show you the addition data set we're going to use to train our sequence to sequence. You can just call this load data by passing addition. And to control the randomness, we're going to pass this seed as well. And when you call this get vocab, this will return child to ID and ID to chart dictionaries. And the shape of the X train is 45,000, 7. And we have 5,000 instances for test. And what does it mean by 7 and 5? Let's have a look at one specific example. And when we run this, this contains a sequence of numbers like this. And what do they mean? Let's visualize what they mean. ID to char. So when we run this one is 71 plus 180, 118. And the result is going to be 189. And to differentiate between the input and the output, we put underbar for the output. And when we also run ID to char, you can see the encoding. Here we have 5 as blank. Here we have 5, 5. Because when we add two three-digit numbers, then we're going to spend 7 spaces. However, when we add 2-digit number and 3-digit number, we have 1 blank. And to make all the sequences have the same length, we put lengths at the end. Similarly, we do the same for the answer. If the answer is 3-digit, we are going to just put 1 blank at the end. If the answer is 4 digits, then we don't have to put blank at the end. Okay? That's how we make all the variable length sequences the same length sequences. Okay? This is the data set we're going to use. And another example is, let's view this one. 206 plus 190. This is going to be 396. And we want our sequence to sequence model to learn these addition process. This one is the input. This one is the expected output. All right. And let's write some training code. So that's the data set we're going to use. Sorry for that. First, we load the data like this. And we define the hyperparameters, word fact size, because we have a small number of vocabularies. We're going to use small word fact size like this. Hidden size is 128. Batch size, because our data set is quite small, we can use a big batch size like this. Max epoch 25, max rod 5.0. Then you can play around with these hyperparameters. You can change or not these values. Here we define our model, sequence to sequence. We pass vocab size, word fact size, and hidden size. And we define optimizer and trainer. We pass model and optimizer. And we're going to collect the accuracies over the epochs. Here, we're going to use max epoch as 1. Why do we need to do this? Because our trainer does not know anything about sequence to sequence. Therefore, we're going to just train one epoch and do evaluation on our own. This is to print out some simple test data. Okay. And we calculate accuracy by dividing the correct number of prediction divided by the total sample data. And to plot the evolution of accuracy, we collect the accuracy of each epoch. And print out the validation accuracy like this. Okay, so here we're using max epoch of 1 because our trainer does not support evaluating sequence to sequence model. This could happen for our implementation using some frameworks, PyTorch or other libraries. If that happens, what we usually do is we just use the part we can use like this. And after that, we insert the custom codes at the end like this. Therefore, when you use some frameworks or libraries, if those libraries or frameworks do not support every functionality you want to use, however, just some part of it, then you just use those frameworks in implementing those some parts. And after that, you implement custom part on your own like this. Okay? And we can also visualize the results. like this. Okay. And when you play around with this code, you'll notice that the performance is not that satisfactory. It's under 20%, the accuracies. And how can you improve this naive implementation of sequence to sequence? We can apply two improvements. The first one is reversing the data. What does it mean? Here, we're adding blanks at the end. And this could somewhat make the distance between encoder and decoder larger. And the information from the encoder or input sequence might not go well to decoder. How can we resolve this issue? We can just reverse this order. So rather than passing this input, we're going to pass 5 first, 11, 0, 0, 2, 0, 3, like this. Pretty simple, right? However, this simple reversing the input and target order greatly improves the performance. And how can we implement that? We can implement that very simply. We're going to introduce is reverse like this. If this one is true, then we're going to reverse the input and output. To reverse all the input sequences, we just put this mark, and it will reverse the order of the list. And we do the same for the target sequence, like this. This simple modification improves the performance greatly. Okay, this is the first modification we can make. Now, what is the second modification we can make? Here we are going to implement improved sequence to sequence. This is what we've discussed in the slides. That is picky sequence to sequence. What is picky sequence to sequence? I'll show you the picture. This is what we've implemented. We pass the input sequence to the encoder, and this encoder encodes the information of the input sequence to the last hidden state. And we pass this last hidden state as the initial state of the decoder RNA or decoder LSTM. And from this hidden state, it receives the start position, start token, and starts to generate characters or words. However, I told you in the slides that this information can be lost easily because this hidden state changes over time. And one resolution to resolve this issue is connecting this or passing this hidden state repetitively to the input sequences over multiple time steps. So every time step, we are going to add the last hidden state of the encoder like this. So here, rather than just inputting the output token, the input token, we're going to concatenate the last hidden state of the encoder with the embedding vector. This is what we did in the slide. However, in this picture, we introduce another path. That is, we also connect this last hidden state of the encoder to this affine layer. So we are concatenating the hidden state of the LSTM with this hidden state, the last hidden state of the encoder. Here, 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 here. Okay? And this architecture is called picky sequence to sequence because every time it generates an output, it picks into the hidden state of the encoder. Okay? And how do we implement picky LSTM? Basically, it's very similar to ordinary sequence to sequence. I'll first copy this decoder and modify this decoder as picky decoder. Okay, this was ordinary decoder. And how can he make this picky decoder? Regarding the encoder, we don't have to change anything. We can just use the same encoder to implement this picky sequence to sequence, as you can see here. Okay, nothing changes for the encoder part. All right. Then what should we change? The first thing is here. LSTM will not just accept the embedding vector. However, it will also accept the last hidden state of the encoder. Therefore, this should not be just D dimension. However, it should also accept the H dimension like this. And for normalization, we need to add H here. And another thing is, for the affine layer, we're going to add another H here because we're going to concatenate the encoder hidden state here to the hidden state of the decoder LSTM. And we add H here as well. So basically, those two things are what we need to change. And another thing we need to introduce here is cache. Okay. Because we have made two additional paths for this H, we need to deal with these two additional paths when we are calculating back propagation. Okay. What about forward? To make this implementation more easy, we're going to first check the shape of the input sequence and the hidden state shape. And we set the initial hidden state of the decoder LSTM as the last hidden state of the encoder, like this. And this is pretty much the same. However, we need to concatenate this embedding vector with this hidden state from the encoder. And to do so, we're going to repeat this. We're going to repeat this hidden state t times, okay, along the axis 0. And we shape this as NTH. And then we are going to concatenate HS and L, this embedding vector and this hidden state from the encoder. And we just need to repeat this H over T time step, capital T time step. We're adding the same H over and over. And the thing is, you don't actually repeat this process. You can use broadcasting. However, to make this process explicit, we are using MP repeat method. Okay? And concatenate these two vectors along axis 2. And we pass this out through this LSTM. And after that, we are going to add this HS once again. Okay? And then we pass through this affine layer. And our H is going to be our cache. And for backward, we need to handle these additional paths. Okay, we collect all the gradients from these paths and add that gradient to this H. That's just what we need to do. So H from cache, and we pass this D score through affine layer. And after that, this affine layer contains two gradients. The first one is for this hidden state from the encoder, and the second one is for this LSTM. So we are going to divide this, the out, as from H to the end, and from first to H. Okay. This is for the hidden state from the encoder. So we should not pass this one to LSTM, but only this one. Okay. So we pass this one through LSTM like this. And after that, this LSTM backward upstream gradient also contains two gradients. The first one is for embedding layer, and the second one is for this hidden state. So we need to divide this upstream gradient into two parts, one for the embedding, the other for the encoding. So we do this process once again. So this one is for embedding layer. This one is for the hidden state. And to this embedding layer, we pass the embed like this. And DHS is going to be DHS 0 plus DHS 1. Okay. This H receives gradients from this path and this path. So we need to add these two gradients. And DH is going to be that from LSTM and by adding DHS along the axis 1. Okay, so this is what we need to additionally implement for PK LSTM. And for generation, we need to think about this shape first. And keep this PKH. So we change the sample ID, the first sample ID is MPRA. And then what we need to do is here, concatenate PKH without the embedding vectors, and then pass this value to LSTM. Okay, after passing the LSTM, we add this PKH once again and pass this value through a affine layer and get score. And then we get another sample ID. Into sampled, we add this sample ID and return. Okay, so we know to change many things for this generate method. Okay, that's how we implement this PK decoder. Okay. Then let's implement PK sequence to sequence by inheriting the ordinary sequence to sequence. Because the behavior of encoder is the same for peaky sequence to sequence and ordinary sequence to sequence. And once we define this peaky decoder, then the interface is pretty much the same. So we don't have to change much. The only thing we need to change is the initializer. VDH for cap size, for back size, hidden size. Decoder, peaky, decoder, VDH, self softmax, time softmax with plus. So these parts are just the same. Okay. Then for other parts like forward, backward, generate, they're just the same. We don't have to change anything. That's why we are inheriting ordinary sequence to sequence here. Okay. So in our training code, we just need to change this part as peaky sequence to sequence. That's all we need to change. Okay. And to introduce reversing the input, we just need to set this variable as true. Okay. So peaky sequence to sequence is here. What's wrong? Sequence to sequence. Oh, we haven't run this code. Okay, so that will solve the problem. All right, and when you run this code, you will see the result. You can compare the results, and I'll show you the results for you because it takes some time to run the code. The results might look like this. So over the epoch, the base ordinary sequence to sequence evolves like this. The accuracy is under like 10%. However, when you just reverse the input order, then the accuracy goes up to like 50 or 60. And when you use peaky sequence to sequence model, the accuracy becomes around 100%. Okay, you can play around with these three models and change the hyperparameters. Okay, this is basic sequence to sequence models.